Today, we're diving into a piece of technology that truly changed the world of medicine, computed tomography, or, as pretty much everyone calls it, the CT scan. This is an incredible story about physics, raw computing power, and a completely new way of looking inside the human body.
But first, let's back up and think about the fundamental challenge doctors have faced for, well, centuries. How do you get a really clear, detailed look at what's going on inside a living person? The organs, the bones, the blood vessels, without actually having to perform surgery? That question is what drove the pioneers of medical imaging.
For a long time, the best answer we had was the X-ray. But a standard X-ray has one huge limitation. It's basically a shadow picture. Everything inside you is flattened and stacked on top of everything else, which gives you this kind of jumbled two-dimensional image. A CT scan, on the other hand, just completely solves that problem. Instead of a shadow, it gives you a clean, cross-sectional slice of the body, getting rid of all that clutter. It's really the difference between looking at a city from space versus having a detailed floor plan for every single building.
So how on earth does this amazing tech slice right through the body without using a blade? Well, that gets us to the core idea behind the whole scan.
The concept is called tomography. It actually comes from two Greek words, tomos, which means a section or a cutting, and graphein, which means to write. So you're literally writing a section. It's all about creating a crystal clear image of a single plane or a slice inside an object.
And here's how it works in practice. First, you have an X-ray source and a detector that spin 360 degrees all the way around you. As that X-ray beam passes through your body, different tissues weaken it, or attenuate it, by different amounts. Bone is really dense, so it blocks a lot of the beam. Soft tissue, not so much. The detector on the other side measures these tiny differences with incredible precision. And this is where the magic really happens. A super powerful computer takes all those measurements from hundreds of different angles and uses some really complex math to figure out the exact density of every single point inside that slice. What you get is a stunningly detailed cross-sectional map of your insides.
Now, the crucial thing to understand is that this isn't just a picture, it's data. Every single point in that image is given a number based on its density, and that value is expressed in something called Hounsfield units, or HU. They're named after Sir Godfrey Hounsfield, one of the geniuses who co-invented the technology and deservedly won a Nobel Prize for it.
And what's really cool is how this scale works. You can see it right here. Think of it like a grayscale paint by numbers for your body. On this scale, air gets a value of -1000, so it shows up jet black. Pure water is the 0 point, it's the baseline. Then you've got soft tissues like muscle and blood in a small positive range, and dense bone is way up there at over 1000, which is why it looks bright white. This level of numerical precision is exactly what lets the computer tell the difference between tissues with such amazing clarity.
But, just creating one static slice wasn't the end of the story. The next big challenge was a race against time itself, a race to get a clearer picture by getting faster and much more precise. See, the problem was motion. The human body is never perfectly still. Your heart is beating, your lungs are breathing, and trying to get a picture of these moving targets with one of the early slow scanners, it was like trying to take a perfectly sharp photo of a hummingbird's wings. Any little movement would just blur the image, creating these artifacts that could totally hide the very thing the doctor was looking for.
The progress over the years has just been mind-blowing. The very first scanner back in 1971, it was revolutionary, but it took about 4 minutes just to get 2 slices of the brain. Then, by the 90s, we got spiral or helical CT. Now the scanner could spin continuously while the patient table moved through, grabbing all the data in one quick go. Then came multidetector CT, which uses tons of detector rows to grab many slices with every single spin. Today, a modern scanner can capture an entire organ in just a fraction of a second. It's incredible.
So, with all this incredible speed and data, the next step was turning all those numbers and slices into something truly powerful for diagnosis. It became all about building a virtual 3D patient.
And the fundamental building block for all of this is something called a voxel. You've heard of a pixel, right? That's a 2D picture element on your screen. Well, a voxel is its 3D cousin. It's a tiny little cube of data that represents a specific volume of your body, and each one has its own unique Hounsfield unit value.
And here's how it all fits together. The scanner grabs one 2D slice, then another, and another, and another, basically stacking them up like pages in a digital book. And once you put all those slices together, what you get is a complete, high-resolution 3D digital model of the patient's anatomy.
And we can even take it a step further. By injecting a special iodine-based contrast dye into the bloodstream, we can make all the blood vessels light up bright white on the scan. This technique is called CT angiography, and it lets doctors create these incredibly detailed 3D roadmaps of your entire vascular system.
So once this 3D model is built, radiologists have this amazing digital toolkit. They can use something called multiplanar reformatting to digitally reslice the data in any direction they want, not just the way it was originally scanned. They can create shaded surface displays to see the outer shape of an organ, or use a tool called a maximum intensity projection, which basically tells the computer, hey, only show me the brightest, densest stuff in this image stack. That is perfect for making things like bone or dangerous plaque in an artery just pop right out.
And the impact in the real world is just immense. CT is absolutely essential for things like detecting aortic aneurysms, quickly checking for internal bleeding after a car crash, staging cancer by showing a tumor's exact size and location, and finding life-threatening blood clots in the lungs. It is, without a doubt, one of the most powerful tools in any modern hospital. But, with any technology this powerful, especially one that uses X-rays, we have to talk about the future, and that means balancing its incredible promise with some necessary precaution.
Of course, there is a big consideration here: radiation risk. The source text we're breaking down today cites an estimate that somewhere between 1.5 and 2% of all cancers in the US might be attributable to radiation from CT scans. That's a sobering number, and it's something the medical community takes very, very seriously.
This risk has led to a really important guiding principle that's supposed to govern every single scan: ALRA. It's an acronym, and it stands for as low as reasonably achievable. The goal is always, to use the absolute minimum amount of radiation needed to get a clear diagnostic image, and not one tiny bit more.
And that brings us right to the future of CT. For decades, the big race was all about getting faster. Now the focus has really shifted. The future is all about getting smarter.
So what does that look like? Well, for one, even lower doses. New, really smart software can take a grainy, low-radiation image and digitally clean it up until it's crystal clear. We call it iterative reconstruction, and it means we get the same great picture with way less radiation. Then there's fusion imaging, where a 3D CT scan taken before surgery is laid right on top of a live X-ray during the operation. It's like giving surgeons a GPS to navigate inside your body. And finally, you have hybrid scanners like PET-CT, which merge the anatomical detail from CT with metabolic info from a PET scan. This shows not just what a tumor looks like, but whether it's actually active and growing.
When you think about it, going from a simple spinning X-ray to a tool that gives surgeons 3D guidance inside the body, CT has just fundamentally changed medicine. It really makes you wonder, as this technology keeps getting faster and safer and smarter, what new mysteries of the human body are we going to solve next?